Welcome to the night. As the world gazes skyward, captivated by headlines screaming about Atlas, that enigmatic interstellar visitor making its grand, distant pass, you might feel a shiver of cosmic awe. But what if the greatest distraction isn't the one grabbing all the attention? Scientists, often quiet observers amidst the clamor, understand that while Atlas poses no threat, another, far less celebrated rock is quietly, relentlessly closing in. Some theories suggest our collective gaze is simply misdirected, while others argue this near miss offers a crucial, overlooked lesson. Join us as we peel back the layers of perception and reality. Let's dive in and explore how it all unfolds. As we journey through the cosmos, seeking answers to the universe's grandest questions, sometimes the answers come to us, quite literally, from beyond. You stand on the precipice of a profound realization as astronomers around the world turn their telescopes to a rare cosmic wanderer, a comet designated 3I Atlas. This isn't just another icy snowball orbiting our sun. It's a true interstellar visitor, a messenger from an entirely different star system. And it has absolutely everyone talking. Imagine a chunk of ice and rock, perhaps forged in the primordial disk of a star system light years away, now streaking through our solar neighborhood. That's 3I Atlas. Its very existence captivates scientists and the public alike because it represents a tangible piece of another cosmic home, a relic from an alien stellar nursery. When it was first spotted, its trajectory immediately signaled something extraordinary. Unlike comets born in our own Oort cloud, which follow elliptical paths bound by the sun's gravity, 3I Atlas traced a hyperbolic orbit, a clear, open curve that unequivocally proclaimed it was merely passing through, never to return. This incredibly high velocity and its definitive, unbound path are the key scientific facts that confirm its interstellar origin, marking it as a cosmic tourist on an unimaginably long journey. But 3I Atlas had a personality, a dramatic flair that added to its mystique. Initially, it presented a dazzling spectacle, rapidly brightening to a degree that ignited hopes for a potential naked eye display, promising a celestial showstopper for observers on Earth. This initial brilliance led to widespread media attention, with headlines speculating about the comet of the century. Yet in a surprising and somewhat poignant twist, this grand performance didn't last. As it drew closer to the sun, its icy nucleus began to fragment dramatically, crumbling into multiple pieces under the increasing warmth and tidal stresses. What started as a potentially magnificent public display transformed into a more intimate, complex scientific study of a dying comet, revealing the harsh realities of interstellar travelers encountering a star for the first time. This fragmentation, while disappointing for public viewing, offered an unprecedented opportunity for astronomers to peer into its interior, studying its composition as its constituent parts broke apart. This rare visit and its dramatic demise raises a profound question that scientists still actively debate. Are such interstellar wanderers truly rare cosmic anomalies, fleeting glimpses of other star systems? Or are they far more common, a constant, albeit mostly unseen, cosmic drizzle of material exchanged between star systems. Some theories suggest our solar system is regularly bombarded by a silent armada of these objects, most too small or too dark to detect, potentially carrying the building blocks of life from one stellar nursery to another. Others argue that while not impossibly rare, large, observable interstellar comets like 3I Atlas are indeed exceptional events, requiring a very specific set of circumstances: a violent ejection from its home system, a long, undisturbed journey through the void, and a chance encounter with our sun to become visible. The very presence of 3I Atlas, regardless of its frequency, offers a unique opportunity to sample material that has never been part of our solar system, providing invaluable clues about the chemical diversity of the galaxy and the processes of planet formation far beyond our familiar cosmic home. As we've explored the vastness of space and the incredible objects that traverse it, a natural question often arises when a new celestial visitor makes headlines. Is it a threat? With Comet Atlas, a name that conjures images of immense, world-bearing power, the answer is a resounding no. Despite its potential grandeur and the initial excitement surrounding its brightening, Comet Atlas, in its current celestial dance, poses absolutely no threat to our terrestrial home. Its closest approach to Earth is meticulously calculated to be a staggering 268 million kilometers away. To truly grasp the scale of that distance, consider this: 268 million kilometers is more than 1.5 times the average distance between Earth and the Sun. Imagine our solar system laid out before you, a cosmic racetrack where planets orbit. At its nearest, Atlas will still be so far out that you could comfortably fit the entire orbit of Mars, that vast, sweeping ellipse between us and the comet. It's not just far, it's an almost incomprehensible gulf, a testament to the sheer, expansive emptiness of space that ensures our safety. This immense distance guarantees that Atlas will simply be a magnificent, if distant, spectacle in our night sky, visible perhaps with binoculars or a small telescope, but certainly not a harbinger of doom. Its gravitational pull will be negligible, utterly incapable of affecting our planet in any measurable way. Its icy particles, even if shed in copious amounts, would be too scattered and diffuse to ever reach our atmosphere, let alone pose a hazard. Its journey is simply a testament to the grand, unhurried movements of the cosmos, unfolding on a stage far beyond our immediate vicinity. The very name Atlas evokes images of the mythical Titan, condemned to bear the weight of the heavens on his shoulders, a colossal, earth-shaking burden. Yet, this celestial namesake, far from bearing down upon us, will merely glide by, a silent, solitary traveler on an ancient path, free of any terrestrial obligations. It's a cosmic irony, perhaps, that something named for such an immense, crushing responsibility will pass with such serene indifference to our world, a graceful, unburdened wanderer. This contrast between its formidable name and its harmless trajectory, we name these objects with our myths and fears, yet they obey only the universal laws of physics, indifferent to our narratives. While the immediate trajectory of Atlas is well established and precisely predicted, the long-term fate and precise physical evolution of such new comets, those making their first or very early passes through the inner solar system after eons in the frigid Oort cloud, remains a subject of intense astrophysical debate. Scientists still debate whether their initial encounters with the sun's intense heat and solar wind significantly alter their volatile composition, potentially leading to more dramatic outbursts, sudden fragmentations, or even complete disintegration on subsequent returns, perhaps millennia from now. Some theories suggest that the thermal shock of solar proximity can indeed crack these icy bodies, causing internal pressures to build and leading to spectacular, unpredictable flares, or even the splitting of the nucleus. Others argue that their deeply frozen primordial structures are far more resilient, capable of enduring countless close encounters with our star with only gradual, surface-level sublimation. This isn't to say Atlas itself is unstable for this pass. Its current behavior is well within expected parameters, but rather that each such visitor offers a unique data point in understanding the grand evolutionary saga of comets. The precise mechanisms by which solar radiation and the solar wind ablate their surfaces, causing those spectacular tales we so admire, are still being refined. Is it a uniform erosion, or are there hidden pockets of highly volatile materials that could suddenly erupt, changing the comet's momentum ever so slightly? These are the subtle nudges and internal dynamics that astronomers painstakingly model, trying to predict not just where a comet goes, but how it changes over cosmic timescales, shaping its destiny across the eons. So, as Atlas continues its majestic sweep through our solar system, you can rest assured that its journey is one of observation, not apprehension. It is a fleeting visitor, a cosmic messenger from the distant reaches of our solar system, offering us a glimpse into the primordial material from which our own world was born, without ever coming close enough to disrupt our tranquil existence. The precision with which we can track such objects, predicting their paths millions of kilometers away, is a testament to the power of modern astronomy and the enduring laws of physics. Gravitational calculations, refined over centuries, allow us to map these celestial dances with astonishing accuracy. From the faintest glimmers caught by ground-based observatories to the sophisticated data gathered by space telescopes, every data point contributes to a complex, three-dimensional map of our cosmic neighborhood. This constant vigilance, this tireless tracking, is what allows us to confidently declare that Atlas, despite its impressive size and dramatic appearance, is merely passing by, a silent, beautiful specter in the inky black, utterly harmless to our blue marble. It's a powerful illustration of cosmic scale, where even a close encounter is still an unimaginable gulf of space, ensuring our safety as we continue to gaze upwards in wonder. As we saw earlier, the universe often presents us with dazzling spectacles, like the comet Atlas, capturing our collective imagination with its ethereal glow and grand cosmic journey. These are the celestial showstoppers, drawing our gaze upwards, filling us with wonder, and sometimes a fleeting sense of vulnerability. But sometimes, the true dangers aren't the ones making headlines or gracing our night skies with such visual splendor. Instead, they are the silent, stony wanderers, unassuming and often overlooked, yet holding a far more direct and tangible threat. This brings us to a celestial body that, despite its profound potential to reshape our understanding of planetary defense, largely flew under the public radar compared to its more flamboyant yet ultimately benign counterparts, the asteroid Apophis. Unlike the icy, dusty beauty of a comet like Atlas, which might offer a stunning celestial performance before fading away, Apophis is a different kind of beast altogether. A solid, rocky chunk of primordial matter, packing a punch far greater than its public profile suggests. You might not have heard its name whispered with the same awe or trepidation as some of the planet killers of Hollywood lore. But Apophis is no ordinary space rock. This roughly 340-meter-wide asteroid, a behemoth roughly the size of 3 football fields laid end to end, is on a collision course with our planet. Not in the sense of an imminent, unavoidable impact, but a truly hair-raising close shave. A cosmic near-miss that will redefine our understanding of orbital dynamics and planetary defense. In 2029, a mere blink of an eye in cosmic time, Apophis will pass closer to Earth than many of our own operational satellites. We're talking about an astonishingly close distance of just 31,000 kilometers from Earth's surface, a mere fraction of the Earth-Moon distance, placing it well within the orbit of geostationary communication satellites that hover some 36,000 kilometers above us. To put that into perspective, if you were in a low Earth orbit, you could practically reach out and touch it. Imagine that, a mountain-sized object, a relic from the solar system's formation, hurtling past us at a staggering speed of over 7 kilometers per second, nearly 25,000 kilometers per hour. For a few precious hours, it will be visible to the naked eye from parts of Europe, Africa, and Asia, as a slow-moving, star-like point of light, a silent testament to the dynamic, sometimes perilous nature of our cosmic neighborhood. Its name, Apophis, is itself a fascinating and somewhat ominous detail, borrowed from the ancient Egyptian god of chaos, darkness, and destruction. A surprisingly apt moniker for an object that, upon its discovery in 2004, briefly held the highest rating on the Torino Impact Hazard Scale. This scale, used by astronomers to categorize the impact hazard of near-Earth objects, assigns a value from 0, no hazard, to 10, certain global catastrophe. Apophis initially reached a level 4, indicating a 1% or greater chance of a localized impact, causing significant regional devastation. Initial calculations, based on limited observational data, suggested a significant chance of impact, sending ripples of concern, even alarm, through the scientific community. For a brief period, the possibility of a direct hit was very real, sparking intense observation campaigns across the globe. Thankfully, subsequent, more precise observations and refined orbital mechanics calculations allowed scientists to rule out a direct hit for 2029, bringing collective sighs of relief. The immediate danger for that year was averted, but the story of Apophis is far from over, and its proximity presents an unparalleled opportunity for scientific study. The real intrigue and the source of ongoing academic tension and tireless research lies in what happens after this unprecedented 2029 flyby. As Apophis swings by Earth, our planet's immense gravitational field will exert a powerful tug, a cosmic slingshot effect, profoundly altering its precise orbital path. Scientists are meticulously tracking a concept known as a gravitational keyhole, a precise, incredibly narrow region in space, only a few hundred meters wide, that Apophis could pass through. Think of it like a cosmic bullseye. If the asteroid threads this infinitesimally small needle, its trajectory would be nudged just so, putting it on a potential collision course with Earth for a future encounter, perhaps in 2068 or even later. The precise mechanics involve highly complex calculations, modeling the gravitational influences of not just Earth, but also the Moon, the Sun, and other planets over decades, accounting for tiny perturbations that could dramatically change the outcome. It's a testament to the power of celestial mechanics and the delicate dance of gravity. Scientists still debate the exact probability of Apophis hitting one of these keyholes and the subsequent long-term impact risk. It's a field where the margin for error is incredibly small, and the stakes, undeniably, are astronomically high. Even if the odds are slim, the potential consequences demand our utmost attention and proactive planning. An impact from an asteroid of Apophis' size wouldn't be a planet-killer event in the extinction-level sense, but it would unleash energy equivalent to hundreds, perhaps thousands, of megatons of TNT, far exceeding the most powerful nuclear weapons ever tested. Such an event would cause devastating regional destruction, triggering catastrophic tsunamis if it hit an ocean, or creating a massive impact crater and widespread atmospheric effects if it struck land, potentially altering climate patterns. The economic, social, and environmental fallout would be catastrophic on a global scale, far beyond anything humanity has experienced in recorded history from a natural event. This isn't science fiction, it's a real, albeit low-probability scenario that demands continuous, painstaking orbital mechanics calculations, advanced telescopic observations, and international collaboration to monitor and, if necessary, develop strategies to mitigate such a threat. The 2029 flyby offers an unprecedented opportunity to study an asteroid up close, to understand its composition and structure, which could be crucial if we ever needed to deflect it. It's a stark reminder that sometimes the greatest threats are not the ones we see coming with a bright, fiery tail, but the ones we're only just beginning to understand, lurking in the shadows of our celestial neighborhood, demanding our vigilant attention and a proactive approach to planetary defense. As we've journeyed through the cosmos, exploring the incredible forces and celestial bodies that shape our understanding of the universe, some objects capture our imagination, not just for their grandeur, but for their very direct connection to our own blue marble. This brings us to a specific, rather infamous space rock, Apophis, the asteroid with a date. Imagine, if you will, a mountain, not one rooted to Earth, but a colossal chunk of rock and metal, roughly 340 meters across, hurtling through the vacuum of space. This is Apophis, a celestial wanderer that has been meticulously tracked since its discovery in 2004. Its orbit is not just a distant path. It is one that guarantees an exceptionally close encounter with Earth. Mark your calendars, because on April 13th, 2029, this enormous asteroid will perform a breathtaking celestial ballet, passing closer to our planet than many of our own geostationary satellites. You might be wondering, just how close is exceptionally close? To put it into perspective, Apophis will sweep past us at a mere 31,000 kilometers from Earth's surface. The Moon, our closest natural companion, orbits at an average distance of nearly 400,000 kilometers. This isn't a near miss in the typical sense. It's a cosmic whisper, a gravitational embrace that will offer an unprecedented opportunity for scientific observation. For a brief window, from certain regions of the globe, Apophis will even be visible to the naked eye, appearing as a faint, moving star. Picture yourself looking up at the night sky and seeing a piece of the early solar system, a potential harbinger of chaos, momentarily visible without the aid of a telescope. It's a profound thought, connecting us directly to the vastness and dynamism of our solar neighborhood. The name Apophis itself carries a fascinating, almost prophetic weight. It's derived from Apep, the ancient Egyptian god of chaos, darkness, and destruction, a fitting moniker for an object that, upon its initial discovery, briefly caused a stir within the scientific community due to a calculated, albeit tiny, non-zero chance of impact. While subsequent observations and refined orbital calculations have firmly ruled out any impact in 2029, the name serves as a potent reminder of the potential for cosmic events to shape our destiny. Yet even with the immediate threat averted, the scientific community isn't entirely relaxed about Apophis. This close flyby presents a unique challenge and opportunity. Scientists still debate the long-term implications of such a close gravitational interaction. Some theories suggest that as Apophis passes through Earth's gravitational field, its trajectory could be subtly yet significantly altered. This leads to the concept of gravitational keyholes, specific, tiny regions in space that, if the asteroid passes through them, could deflect its path just enough to put it on a collision course for a future encounter, perhaps in 2068 or beyond. Other models, however, argue that the precise nature of these keyholes and the likelihood of Apophis hitting one are still subject to significant uncertainty. The complex interplay of gravitational forces from Earth, the Moon, and even the Sun makes long-term orbital predictions incredibly challenging, introducing an academic tension that drives ongoing research. Beyond its trajectory, scientists also grapple with understanding Apophis's internal structure and material density. Is it a solid, monolithic rock, or more akin to a rubble pile, a loosely bound collection of smaller rocks and dust? This isn't merely an academic curiosity. It's a crucial piece of the puzzle for developing effective planetary defense strategies. Should humanity ever need to nudge a similar object off course, the method employed, whether a kinetic impactor, a gravitational tractor, or something entirely different would depend heavily on knowing what we're dealing with. Some researchers propose that a solid object might fracture unpredictably, while a rubble pile could absorb impact energy differently, requiring a more gentle, persistent nudge. The debate continues, fueling missions like NASA's OSIRIS-REx and Japan's Hayabusa 2, which gather vital data from other asteroids to inform our understanding. The 2029 flyby of Apophis therefore becomes more than just a spectacle. It's a live laboratory. Telescopes and radar systems across the globe will be trained on this celestial visitor, gathering unprecedented data on its shape, rotation, composition, and how its orbit is truly perturbed by Earth's gravity. This builds on our earlier discussions about the importance of observational astronomy and orbital mechanics. Every piece of information gleaned will refine our models, enhance our predictive capabilities, and ultimately bolster our planetary defense readiness. It's a testament to human ingenuity and our relentless pursuit of knowledge, turning a potential threat into an extraordinary learning opportunity. This close encounter serves as a powerful reminder of our place in the cosmos, not just as inhabitants of a fragile world, but as active observers and, increasingly, as potential stewards of our celestial neighborhood. As we've journeyed through the cosmic ballet of our solar system, understanding the intricate forces that shape its movements and the celestial bodies that dance within it, one upcoming event stands out for its sheer, breathtaking proximity. We're talking about an asteroid, a substantial chunk of rock known as Apophis, which is set to sweep past our home planet at an astonishingly close distance. On April 13th, 2029, this celestial visitor will be just 31,000 kilometers above Earth's surface. To truly grasp the profound significance of this number, let's cast our gaze upwards, beyond the clouds, to the invisible ring of geosynchronous satellites that faithfully orbit our world. These are the silent workhorses of our modern communication infrastructure, positioned at a precise altitude of approximately 35,786 kilometers. From our perspective on the ground, they appear almost stationary, a testament to their orbital period perfectly matching Earth's rotation. These technological marvels provide the backbone for everything from your live sports broadcasts and global telecommunications to critical weather data, navigation signals, and the very internet connectivity that powers much of our daily lives. They are essential arteries of the digital age. Now, imagine an object, a natural, untamed visitor from the deep solar system that will not merely pass by this vital orbital highway, but will actually slice beneath it. Apophis will venture into a region of space typically reserved for our most advanced technological creations, a domain we consider our immediate cosmic backyard. To put its size into perspective, Apophis measures approximately 340 meters, or 1,100 feet across. That's roughly the length of 3 American football fields laid end to end, or the height of a small skyscraper, a colossal rock tumbling through the vacuum. Imagine an object of that magnitude hurtling through the space between your television satellite and the Earth. That's the extraordinary scale of this upcoming encounter. This isn't just any close pass. It marks the closest flyby of such a substantial asteroid in recorded history. We're not talking about a tiny pebble that would burn up unnoticed in the atmosphere. This is an object large enough to be seen with the naked eye from certain parts of the world, particularly in the Eastern Hemisphere, appearing as a fast-moving, star-like point of light for a brief, unforgettable period. Its sheer speed, approximately 7.5 kilometers per second, or over 16,700 miles per hour, will make it a truly dynamic spectacle, far quicker than any human-made satellite you might spot. For a fleeting moment, Apophis will be closer to you than Los Angeles is to New York City. If you could somehow drive straight up into space, it will be closer than the International Space Station, closer than many low Earth orbit satellites. It's an unprecedented peek into our cosmic neighborhood. This extraordinary proximity offers an unparalleled opportunity for scientific study, transforming what was once a source of concern into a goldmine of data. Researchers worldwide are already preparing, with immense anticipation, eager to deploy an array of instruments, from powerful ground-based radar and optical telescopes to potentially even small, dedicated space probes, to gather as much information as possible as Apophis streaks by. What secrets will its ancient, cratered surface reveal under such close scrutiny? Can we map its precise shape, measure its density, and analyze its composition in unprecedented detail? How will Earth's powerful gravitational field subtly tug and alter its trajectory? A cosmic billiard shot playing out in real time. This brings us to a fascinating academic tension that has captivated planetary scientists for years. The precise, long-term prediction of Apophis's future path. When Apophis was first discovered in 2004, initial orbital calculations, based on limited data, assigned it a surprisingly high probability of impacting Earth in 2029. This sparked a flurry of scientific activity, public concern, and even speculative headlines. However, as more observational data was gathered and tracking became more precise, scientists were able to refine their models, definitively ruling out an impact for the 2029 flyby. This journey from initial alarm to precise certainty beautifully illustrates the power and iterative nature of the scientific method. Yet the story doesn't end there. Scientists still meticulously debate the exact implications of Apophis's passage through various gravitational keyholes during its 2029 encounter. These are infinitesimally small, specific regions in space. Think of them as cosmic bullseyes, where Earth's gravity could, in theory, nudge Apophis onto a trajectory that might lead to an impact many decades later, perhaps in 2068 or beyond. Some researchers tirelessly focus on the intricate modeling of these keyholes, understanding that even a slight deviation in Apophis's path during this close approach could have profound effects on its future orbital evolution, potentially shifting its trajectory into or out of a future collision course. They explore the statistical probabilities, the margins of error, and the long-term chaotic dynamics at play. On the other hand, other scientists argue that while the concept of gravitational keyholes is a crucial aspect of orbital mechanics and planetary defense, the probability of hitting such a precise keyhole for a future impact remains exceptionally low. They emphasize that the sheer vastness of space, combined with the continuous refinement of observational data, makes a future impact highly improbable, advocating for continued, precise monitoring rather than exaggerated alarm. They highlight the incredible difficulty in predicting these minute gravitational interactions with absolute certainty over centuries, a testament to the complex, chaotic nature of orbital dynamics and the incredible precision required to map the future paths of our celestial neighbors. Regardless of these ongoing debates, this close encounter serves as a powerful, tangible reminder of the dynamic, ever-changing environment of our solar system. It underscores our ongoing quest to understand its intricate mechanics, to refine our predictive capabilities, and to develop strategies for planetary defense. Apophis, once a symbol of potential threat, has transformed into an unparalleled natural laboratory, offering humanity a front-row seat to a truly extraordinary cosmic event. Imagine a shadow, not of a cloud, but of rock and metal, hurtling through the vacuum of space. As we've explored earlier, the universe is a shooting gallery, and sometimes the targets are planets like ours. Now, let's confront the stark reality of what a truly significant impact would mean. Picture a celestial body, roughly 340 meters across, about the length of 3 football fields, on a collision course with Earth. You stand on the precipice of understanding a cataclysm that, while rare, is a defining force in planetary history. The moment of impact would unfold with terrifying speed and unimaginable energy. If it struck land, the kinetic energy released would be equivalent to thousands of megatons of TNT, far surpassing the combined yield of all nuclear weapons ever detonated. The initial blast would vaporize everything within a radius of many kilometers, carving out a crater dozens of kilometers wide and several kilometers deep. Seismic waves, far more powerful than any earthquake, would ripple across continents, triggering widespread devastation, collapsing structures, and potentially igniting immense wildfires across vast regions. The air itself would turn into a superheated, incandescent plasma, a searing wave of destruction expanding outwards at supersonic speeds, flattening forests and cities alike for hundreds of kilometers. Should this colossal object plunge into the ocean, the consequences would be equally, if not more, terrifying. The impact would create a transient cavity in the water, miles wide, followed by an enormous column of superheated steam and water vapor rocketing into the atmosphere. Moments later, the ocean would rush back in, generating colossal tsunamis that would dwarf anything recorded in human history. These waves, potentially hundreds of meters high, would race across entire ocean basins, inundating coastlines and low-lying areas with unimaginable force, wiping out infrastructure and claiming millions of lives across multiple continents. The sheer scale of the displacement would inject vast quantities of salt water and sediment into the atmosphere, potentially altering weather patterns for years. To grasp the magnitude, consider known events in Earth's history. The 1908 Tunguska event, caused by an object estimated to be only 50 to 60 meters across, flattened 2,000 square kilometers of Siberian forest. A 340-meter asteroid is orders of magnitude larger, carrying exponentially more destructive power. While not a global extinction event like the Chicxulub impactor that ended the reign of the dinosaurs, an object estimated to be 10 to 15 kilometers wide, a 340-meter impact would undoubtedly be a regional catastrophe on a continental scale, with global repercussions for climate, food supply, and human civilization. Scientists still debate the exact long-term climatic cascade that such an event would trigger, from dust-induced impact winters to greenhouse gas releases from vaporized rock, but the consensus is clear. The immediate aftermath would be a period of immense suffering and environmental upheaval. Yet a quirky detail often overlooked is the sheer geological artistry of such events. The immense pressures generated can literally transform carbon into impact diamonds, tiny glittering testaments to cosmic violence embedded within the shattered rock. The risk is immense, the potential for loss staggering, reminding us that our planet's history, and indeed its future, is inextricably linked to the unpredictable dance of objects in space. As we journey deeper into the cosmic tapestry, we encounter objects that tell vastly different stories, yet both capture our imagination for their unique roles in the grand celestial drama. Imagine for a moment two distinct wanderers, each a testament to the universe's boundless variety, each observed with a blend of scientific rigor and human awe. On one hand, we have Comet Atlas, a fleeting interstellar visitor, and on the other, the notorious asteroid Apophis, a homegrown giant from our own cosmic neighborhood. Consider Comet Atlas, formally designated C/2019 Y4. Discovered in December 2019, it initially promised a spectacular show, potentially becoming visible to the naked eye. What truly set Atlas apart, however, was not just its potential brightness, but its trajectory. Scientists quickly determined that Atlas was not a native of our solar system. It was an interstellar comet, a cosmic nomad hailing from beyond the sun's gravitational dominion. This makes it a rare and precious find, a messenger from another star system, carrying clues about the chemistry and conditions of a distant stellar nursery. You stand on Earth, gazing at a streak of light that has traversed unimaginable distances, a silent, harmless witness to the vastness of space. Its journey, an epic spanning millennia, brings it briefly into our view before it slingshots back into the interstellar void. A ghost from another galaxy, offering a tantalizing glimpse into the universe's diverse building blocks. Its very presence challenges our understanding of how common such interstellar travelers might be, hinting at a constant exchange of material between star systems. Contrast this with 99942 Apophis, an object whose very name evokes a sense of impending doom. Named after the ancient Egyptian god of chaos, Apophis first burst into public consciousness in 2004, when initial calculations suggested a terrifyingly high probability of impact with Earth in 2029. For a time, this near-Earth asteroid became the poster child for planetary defense, a stark reminder of the destructive power lurking in our cosmic backyard. Imagine the frenetic energy in observatories worldwide, the sleepless nights of astronomers as they refined their orbital models, the palpable tension as humanity faced a potential existential threat. This was no distant, harmless visitor. This was a colossal rock, hundreds of meters across, projected to pass uncomfortably close, raising the specter of global catastrophe. The sheer scale of the initial perceived risk, a 2.7% chance of impact, was enough to galvanize a new era of asteroid tracking and deflection research. The key scientific event here was the meticulous re-evaluation of Apophis's orbit. Through dedicated observation campaigns and increasingly sophisticated computational models, scientists were able to significantly refine their predictions. The initial alarm, while justified by the data available at the time, gradually subsided. By 2021, NASA officially ruled out any impact risk for at least the next century, including its much-anticipated close approach on April 13, 2029. On that date, Apophis will pass within 32,000 kilometers of Earth, closer than some geostationary satellites. While still a remarkably close shave, it will be a spectacular flyby, not a catastrophic collision. This dramatic shift from potential world-ender to celestial spectacle highlights the incredible precision and ongoing refinement of modern astrodynamics. This brings us to an academic tension that continues to fuel research: the long-term predictability of asteroid trajectories. While Apophis's immediate threat has been mitigated, the subtle gravitational nudges from planets, the Yarkovsky effect, where sunlight unevenly heats an asteroid, causing a tiny thrust, and even collisions with smaller debris, can subtly alter an object's path over centuries. Scientists still debate the extent to which these minute forces can accumulate and drastically change impact probabilities over extended timescales. Some theories suggest that even seemingly insignificant perturbations could lead to unexpected close encounters far into the future, while others argue that current models are robust enough to account for most known variables. The challenge lies in predicting the unpredictable, in modeling the chaotic dance of gravity and light across vast cosmic distances. So, while Comet Atlas offered us a serene, fleeting glimpse of interstellar wonder, a harmless whisper from another star, Apophis served as a potent, if ultimately benign, wake-up call. It forced us to confront our vulnerability, to hone our observational skills, and to develop strategies for planetary defense. One fascinates for its exotic origins, a beautiful mystery sailing through the dark. The other commands attention for its proximity, a stark reminder of our place in a dynamic, sometimes dangerous, cosmic neighborhood. Both, in their own way, expand our understanding of the universe, urging us to look up, to learn, and to prepare for whatever celestial visitors may come our way. As we delve deeper into the cosmic ballet, sometimes a dancer comes uncomfortably close, demanding our full attention. Imagine yourself in December 2004 as astronomers at the Catalina Sky Survey, diligently scanning the night sky, make a startling discovery. They identify a new asteroid, initially designated 2004 MN4, a seemingly unremarkable speck of light. But the universe, as you know, often holds dramatic surprises. Almost immediately, initial orbital calculations for this new object begin to paint a concerning picture. Its path suggests an alarmingly close encounter with Earth in 2029. The scientific community springs into action, and as more data pours in, the probability of impact for that year begins to climb. For a brief, terrifying period, this asteroid, soon named Apophis after the ancient Egyptian god of chaos and destruction, registered an unprecedented level 4 on the Torino scale, a measure of potential impact hazard. This wasn't just a theoretical threat, it was a looming shadow, a celestial bullet with our planet in its crosshairs. Just 25 years away. You can almost feel the collective breath held across the globe as scientists raced against time to refine their predictions. This is where the meticulous, relentless work of science truly shines. With every new observation, every faint flicker of light captured by telescopes around the world, Apophis's trajectory became clearer. The initial, alarming impact probability for 2029 began to dwindle, slowly but surely. Imagine the tension in those control rooms, the late-night shifts, as teams crunched numbers, cross-referenced data, and meticulously mapped the asteroid's precise path. Eventually, the good news arrived. Apophis would miss Earth in 2029. A collective sigh of relief echoed through the scientific community and indeed around the world. But Apophis wasn't done with its dramatic performance. Even as the 2029 impact risk evaporated, a new, more nuanced concern emerged. Scientists realized that a very close pass by Earth in 2029 could still be problematic. If Apophis were to fly through a specific, incredibly narrow region of space, a gravitational keyhole, during its close approach, Earth's gravity could subtly alter its orbit, nudging it onto a collision course for a later date, specifically 2036. This wasn't a direct hit, but a cosmic billiard shot, where one near miss could set up another, more dangerous encounter. This quirky, lesser-known detail of orbital mechanics highlighted the intricate dance between celestial bodies and the terrifying precision required for long-term prediction. The stakes remained high. More observations were crucial, including painstaking radar measurements that could pin down Apophis's position and velocity with unparalleled accuracy. These efforts, a testament to global scientific collaboration, eventually confirmed that Apophis would indeed miss the gravitational keyhole in 2029, thereby posing no threat in 2036 either. The immediate danger had passed, and the god of chaos would, for now, remain a distant observer. Yet, the warning Apophis delivered remains unforgettable. It was a profound wake-up call, a stark demonstration of how quickly a potential planetary threat can emerge, and how vital our global network of asteroid hunters and orbital calculators truly is. It galvanized efforts in planetary defense, pushing us to develop better tracking systems, refine our computational models, and even consider future deflection strategies. While the immediate threat from Apophis has been mitigated, scientists still meticulously track it, along with countless other near-Earth objects. The academic tension lies not just in finding these objects, but in the enduring challenge of accurately predicting their paths over centuries, a task demanding ever-increasing precision and vigilance, especially for those objects whose orbits are influenced by planetary gravitational tugs. Apophis, the ancient bringer of chaos, ultimately brought clarity, a sharp reminder that our cosmic neighborhood is dynamic, and our proactive understanding of it is paramount for our future. As we've seen, the discovery of Apophis sent ripples of concern through the scientific community and beyond. But the story doesn't end with its initial identification. It's here, in the meticulous, painstaking work of tracking, that humanity truly rises to meet the cosmic challenge. You stand now at the heart of a global vigil, a network of eyes and ears constantly scanning the void. Imagine a colossal game of cosmic hide-and-seek, played out on an astronomical scale. This is the daily reality for institutions like NASA's Jet Propulsion Laboratory, JPL, and its Center for Near-Earth Object Studies, CNEOS, with its Near-Earth Object Coordination Center, NEOSC. From their mission control centers and data hubs, these agencies orchestrate a symphony of observations, pulling together data from observatories scattered across our planet. The initial sightings of Apophis, like many near-Earth objects, came from optical telescopes, vast light-gathering instruments that pinpoint a moving speck against the starry backdrop. These early observations provide a rough sketch of an asteroid's path. But to truly understand its intentions, to predict its future with the kind of precision needed for planetary defense, we need something more. This is where radar imaging steps in, transforming fuzzy points of light into detailed, three-dimensional portraits. Picture the colossal dish of the Goldstone Solar System radar in California, or the now silent but historically vital Arecibo Observatory in Puerto Rico, beaming powerful radio waves across millions of miles of space. These waves bounce off Apophis, returning faint echoes that are then meticulously analyzed. It's like using sound waves to map the inside of a cave, but on an interstellar scale. These radar echoes reveal not just the asteroid's precise distance and velocity, but also its shape, size, and even its rotation rate. This is a key scientific fact. Radar observations dramatically reduce the uncertainty in asteroids' orbit, often by orders of magnitude, turning a potential path of hundreds of thousands of kilometers into a corridor just a few hundred meters wide. For Apophis, these radar measurements, particularly those taken during its 2013 close approach, were instrumental in definitively ruling out an impact in 2029, a moment that had once carried a 2.7% chance of collision. But the universe, as you know, is a place of subtle forces. While gravity is the dominant sculptor of orbits, there are other, more elusive influences at play. Here's a quirky detail that often goes unnoticed. The Yarkovsky effect. This tiny asymmetric push acts like a minuscule thruster, subtly altering the asteroid's trajectory over decades and centuries. It's a whisper in the cosmic wind, but one that can significantly shift long-term predictions, especially for smaller objects. Understanding and modeling the Yarkovsky effect is crucial for pinpointing an asteroid's path far into the future. This brings us to an academic tension phrase. While the immediate threat of Apophis for 2029 has been confidently dismissed, thanks to these precise measurements, scientists still debate the long-term predictability of all potentially hazardous asteroids, especially when considering the cumulative, often unpredictable effects of phenomena like the Yarkovsky effect and other non-gravitational perturbations. Some argue that the inherent chaotic nature of orbital mechanics, even with the best data, places fundamental limits on absolute certainty over millennia, while others maintain that continuous, high-precision tracking and ever-improving computational models will eventually allow us to map out virtually all significant future close approaches with high confidence. The data pouring in from optical telescopes and radar facilities worldwide is fed into sophisticated computational models. These models don't just calculate a simple parabolic arc. They account for the gravitational tugs of the Sun, Jupiter, Saturn, and every other significant body in our solar system. They even factor in the tiny, almost imperceptible pull of other asteroids. Every new observation refines the model, narrowing down the margin of error, painting an ever clearer picture of Apophis's journey. It's a continuous, collaborative effort. Amateur astronomers contribute valuable data, their observations often filling gaps in professional telescope schedules. Each data point, no matter how small, adds another brushstroke to the grand cosmic portrait. This global vigilance ensures we understand Apophis's trajectory precisely, not just for the next few years, but for decades, even centuries, into the future. It allows us to identify any potential keyholes, tiny regions in space that, if Apophis were to pass through them during a close encounter, could gravitationally deflect it onto an Earth-impacting trajectory in a subsequent orbit. For Apophis, the meticulous tracking has shown that it will safely miss all known keyholes during its 2029 close pass. This ongoing observation is more than just a scientific exercise. It's an act of planetary stewardship. By understanding the precise movements of objects like Apophis, we move beyond simply reacting to threats. We gain the knowledge and the lead time to potentially mitigate them, transforming a cosmic hazard into a celestial clockwork we can predict and understand. It's a testament to human ingenuity and our collective commitment to safeguarding our pale blue dot. As we've journeyed through the vastness of space and the intricate dance of celestial bodies, a particular year looms large on humanity's calendar: 2029. It's a date that, for many, might seem distant. Yet for astronomers and planetary defense experts, it represents an unprecedented historic moment. This isn't just another calendar entry. It's when humanity will collectively hold its breath and look up, witnessing a spectacle unlike anything seen in modern history. Imagine, if you will, the night sky not just adorned with stars and the familiar glow of the moon, but with a new, moving point of light. an object that for a brief, astonishing period will be visible to the naked eye. This is the promise of April 13th, 2029, when the asteroid 99942 Apophis will make an exceptionally close approach to Earth. To put this into perspective, Apophis is roughly 340 meters, about 1,100 feet across, a truly colossal space rock, comparable in size to 3 football fields. Its passage will bring it closer than some of our geostationary communication satellites, skimming past our planet at a mere 31,000 kilometers, 19,000 miles above the surface. To truly grasp this proximity, consider that the moon is nearly 400,000 kilometers away, making Apophis's flyby more than 10 times closer than our nearest natural neighbor. This isn't merely a close shave. It's a front row seat to a cosmic ballet. For the first time in modern history, a giant asteroid of this magnitude, one that could cause significant regional devastation if it were to strike, will pass so near that you won't need a telescope to see it. From parts of Europe, Africa, and Asia, Apophis will appear as a slow-moving star, traversing the sky over several hours. It will be brighter than many familiar stars, potentially reaching a magnitude of 3.1, making it easily discernible even from moderately light-polluted areas. This direct, unassisted observation by millions, perhaps billions of people, is an event unparalleled in recorded human experience. The sheer improbability of such an event occurring within the span of recorded human observation, and at a time when we possess the scientific instruments to study it in detail, is nothing short of astounding. Think of all the asteroids that have passed by over millennia. For this particular one, named after the ancient Egyptian god of chaos and destruction, to offer such a unique viewing opportunity is a peculiar twist of cosmic fate. Almost as if the universe itself is putting on a show, scientists are, of course, buzzing with anticipation. This flyby offers an unparalleled chance to study a large asteroid up close without the expense and complexity of a dedicated sample return mission. Ground-based radar observatories like Goldstone, alongside powerful optical telescopes, will track Apophis with unprecedented precision. These instruments will map its surface with incredible detail, revealing its precise shape, its rotation rate, and potentially its internal structure through subtle gravitational variations. Moreover, spacecraft like NASA's OSIRIS-APEX, formerly OSIRIS-REx, are even being redirected to rendezvous with Apophis shortly after its flyby, providing an even more intimate look at this celestial visitor. OSIRIS-APEX will spend months orbiting Apophis, studying its surface changes, searching for signs of seismic activity induced by Earth's gravity, and analyzing its regolith, the loose surface material, which could be disturbed by the close encounter. This mission will provide invaluable data on how an asteroid's physical properties respond to a strong gravitational interaction. Yet, despite the excitement, academic tension remains. While the immediate risk of an impact in 2029 has been definitively ruled out through precise orbital calculations, the long-term implications are still a subject of ongoing study and intense debate. Scientists still debate the exact extent to which Earth's powerful gravitational field will subtly alter Apophis's trajectory. This gravitational keyhole effect, as it's known, is a concept where even a slight deflection during a close pass through a specific narrow region in space could, over decades, nudge an asteroid onto a different, potentially more hazardous path for future encounters, perhaps in 2068 or beyond. The challenge lies in predicting these minute changes with absolute certainty, as even tiny uncertainties in Apophis's mass distribution or the precise nature of its interaction with Earth's gravity could lead to diverging outcomes over long timescales. Some theories suggest the gravitational tug could induce asteroid quakes on Apophis, potentially reshaping its surface, triggering landslides, or even altering its spin rate and overall stability. While others argue these effects might be negligible, or at least predictable enough to mitigate. The exact composition of Apophis, whether it's a solid monolith, a porous rubble pile, or something in between, also significantly influences how it might respond to Earth's gravity, further complicating long-term predictions. Understanding these subtle interactions is crucial for refining our predictive models and, ultimately, for developing effective planetary defense strategies. The 2029 flyby is not just a show, it's a critical learning opportunity, a real-world experiment playing out before our very eyes, offering insights that could one day safeguard our planet. It's a moment when the abstract concepts of orbital mechanics and planetary defense become tangible, visible to everyone, sparking both wonder and a profound sense of scientific responsibility. As we've grappled with the sheer scale and potential implications of the Apophis encounter, a cosmic near miss that, as we discussed, once registered as a significant, albeit fleeting, concern, a powerful new perspective emerges. The very proximity that once sparked apprehension now ignites an unparalleled scientific curiosity, transforming a potential threat into an unprecedented, live laboratory experiment. This isn't just about breathing a sigh of relief. It's about seizing an extraordinary educational opportunity, a chance to glean secrets from the heart of our solar system. Indeed, the astronomical community isn't merely watching from afar. It's actively planning spacecraft missions, spearheaded by the repurposed OSIRIS-REx mission, now brilliantly renamed OSIRIS-APEX for Apophis Explorer, are already charting courses to rendezvous with this celestial wanderer. Imagine, if you will, a robotic explorer, a marvel of human ingenuity, drawing near this cosmic traveler, its advanced instruments poised to peel back layers of mystery. These missions aim to observe Apophis up close, scrutinizing its fundamental composition. What is it truly made of? Is it rich in silicates, hinting at a stony origin? Does it contain metals, suggesting it might be a fragment of a larger differentiated body? Or perhaps even traces of water-bearing minerals, offering clues about the early solar system's volatile delivery mechanisms. High-resolution cameras will map its surface with astonishing detail, while spectrometers will analyze its light, revealing its chemical fingerprint. Beyond composition, These missions will meticulously study Apophis's intricate structure. Is it a solid, monolithic block, a single, sturdy piece of rock? Or, as many asteroids are suspected to be, is it a rubble pile? A loose aggregation of smaller rocks, boulders, and dust, held together primarily by its own weak gravity, like a cosmic sandcastle. Understanding this internal architecture is critical, and the upcoming flyby offers a unique, dynamic test case. Radar imaging will probe beneath its surface, searching for voids, density variations, and the telltale signs of its internal arrangement. But the truly unique aspect, the golden ticket for scientists, lies in Apophis's intimate dance with Earth's gravity during its 2029 close approach. As it hurtles past our planet, a mere 32,000 kilometers above the surface, closer than some geostationary satellites, our colossal gravitational pull won't just tug at it. It will perform a profound cosmic kneading. Think of it like a baker gently yet firmly reshaping a lump of dough, or the way the moon's gravity stretches and deforms Earth, creating our ocean tides. Earth's immense tidal forces will stretch and squeeze Apophis, potentially altering its very form. You might envision a slightly elongated sphere becoming more egg-shaped, or even developing subtle bulges along its equator, a visible testament to our planet's gravitational embrace. This isn't just about surface deformation. It's about a dynamic interaction that could ripple through its entire being. Scientists are particularly keen to understand if this gravitational massage could trigger asteroid quakes, internal shifts, or even cause material to shed from its surface, creating a temporary, faint halo of debris. It's a rare chance to witness planetary mechanics in action, a live demonstration of how celestial bodies interact, without having to wait eons for geological processes to unfold. This encounter represents a natural experiment on an astronomical scale, offering insights into asteroid mechanics that could otherwise only be theorized through complex simulations. Imagine the data, before and after observations, revealing the subtle, or perhaps not so subtle, changes induced by a planetary flyby. This is a front-row seat to cosmic evolution, playing out in real time, right in our celestial neighborhood. However, the precise extent and nature of this reshaping remain subjects of intense academic debate. While some sophisticated computer models predict a significant, measurable deformation, possibly elongating Apophis by several meters, others suggest that if Apophis is indeed a rubble pile, it might absorb these stresses differently, perhaps settling into a new equilibrium with minimal outward change, or even causing internal rearrangement without drastic external deformation. Scientists still debate whether this encounter will merely bruise Apophis, causing minor surface alterations and perhaps some internal settling, or fundamentally rearrange its internal architecture, potentially exposing pristine, untouched material from its interior. Will it be a gentle, elastic squeeze, or a more dramatic, plastic deformation that permanently alters its core? The answers will profoundly influence our understanding of asteroid dynamics, This profound shift in perspective, from apprehension to anticipation, echoes our broader journey through the cosmos, just as we've learned to decode the faint whispers from distant galaxies. We are now poised to listen to the rumble of an asteroid being reshaped by our own planet's gravitational song. By understanding how Apophis responds to our gravity, we gain crucial knowledge about the structural integrity and dynamic behavior of near-Earth objects in general. This data is invaluable not just for the pure pursuit of scientific knowledge, but for the practical applications of planetary defense. If we ever need to deflect an asteroid, knowing how it might react to external forces, even the subtle gravitational nudges of a passing planet, or the targeted impact of a kinetic deflector, is absolutely paramount. It's about understanding the very fabric of these cosmic travelers, preparing us for future interactions. Be they benign encounters or potentially hazardous threats. The danger in a twist of cosmic irony has become our greatest teacher, offering a front-row seat to the dynamic processes that sculpt our solar system and, by extension, influence our own fate. As we navigate the vast cosmic ocean, we've come to understand that Earth is not an isolated island, but a target in a celestial shooting gallery. For millennia, the threat of incoming objects was a matter of myth and sudden, inexplicable catastrophe. But in the early 21st century, a specific celestial body brought this ancient fear into sharp scientific focus. Asteroid 99942 Apophis, discovered in 2004. Apophis quickly became a household name in astronomical circles, and for a brief, tense period in the public imagination. Initial calculations, based on limited observational data, suggested a surprisingly high probability, as high as 2.7%, that Apophis could impact Earth in 2029. Imagine, for a moment, the scientific community grappling with such a number. It was an unprecedented moment, forcing us to confront a threat that had long been relegated to science fiction: a significant, imminent asteroid impact. This wasn't just another distant rock. Apophis was estimated to be around 370 meters, about 1,200 feet, across. An impact from an object of that size wouldn't cause a global extinction event like the dinosaur killer, but it would unleash energy equivalent to hundreds of megatons of TNT, devastating a region the size of a small country, and sending tsunamis across oceans if it hit water. The sheer scale of potential destruction galvanized researchers, engineers, and policymakers worldwide. It was a wake-up call, a celestial alarm bell ringing across the planet. Even as further observations refined Apophis's orbit, reducing the 2029 impact probability to 0, and subsequent analyses ruled out any impact for at least the next century, the Apophis scare had already served its purpose. It transformed planetary defense from a fringe concept into a serious, well-funded scientific endeavor. The theoretical discussions about deflecting asteroids suddenly gained urgency. We moved from what if to how do we. One particularly intriguing and slightly unnerving aspect of the Apophis story involved what scientists call a gravitational keyhole. This isn't a physical keyhole in space, but a tiny region in space, only a few hundred meters wide, that Apophis could have passed through during its 2029 close approach. If it had passed through this precise keyhole, Earth's gravity would have subtly altered its trajectory, just enough to ensure a collision on a subsequent pass, perhaps in 2036. The precision required for such a cosmic billiard shot highlights the delicate dance of orbital mechanics and the potential for seemingly minor interactions to have profound future consequences. The challenge was monumental. How do you move an object weighing millions of tons, traveling thousands of miles per hour, with enough precision to steer it away from a collision course? Scientists proposed various methods. Kinetic impactors, where a spacecraft slams into the asteroid to alter its momentum. Gravity tractors, which use the subtle gravitational pull of a nearby spacecraft to tug the asteroid off course over time. And even nuclear detonations, designed to vaporize part of the asteroid's surface, creating a propulsive force. Each approach had its own set of complexities, technological hurdles, and ethical considerations. The scientific community had to balance the urgency of developing a solution with the immense responsibility of manipulating celestial mechanics on a grand scale. The very idea of humanity intentionally altering the path of a celestial body was, until recently, pure fantasy. Fast forward to September 2022, and humanity achieved a monumental first. NASA's Double Asteroid Redirection Test, or DART mission, deliberately crashed a refrigerator-sized spacecraft into Dimorphos, a small moonlet orbiting the larger asteroid Didymos. This wasn't a hypothetical exercise. It was a real-world demonstration of a kinetic impactor, a direct test of humanity's ability to defend itself. The DART spacecraft, traveling at approximately 22,500 kilometers per hour, 14,000 miles per hour, slammed into Dimorphos, creating a spectacular plume of ejected material visible from Earth. This wasn't just a blind hit. It was a carefully orchestrated experiment designed to measure the precise effect of the impact. The result? Stunningly successful. Observations from ground-based telescopes and the advanced capabilities of the Hubble and James Webb Space Telescopes confirmed that DART had indeed altered Dimorphos's orbit around Didymos. Its orbital period was shortened by 33 minutes, far exceeding the minimum success threshold of 73 seconds. This wasn't just a minor nudge. It was a measurable, predictable, and significant change in a celestial body's trajectory, achieved by human ingenuity. The mission proved that the kinetic impactor concept is not only viable, but remarkably effective for objects of Dimorphos's size. It demonstrated our capacity not just to observe, but to intervene, to literally shift the course of a celestial object. The DART mission provided irrefutable proof of concept. We now know with certainty that we possess the technology and the understanding to redirect smaller celestial bodies. This is a profound shift in our relationship with the cosmos. For the first time in our history, we have demonstrated the capacity to actively defend our planet from an existential threat originating beyond our atmosphere. It's a testament to what focused scientific effort, international collaboration, and a clear vision can achieve when spurred by a clear, albeit initially frightening, challenge. It underscores a growing sense of responsibility, moving us beyond mere survival to proactive stewardship of our cosmic environment. However, the DART mission, while a triumph, also highlighted the complexities and the ongoing work ahead. Dimorphos was relatively small, about 160 meters, 525 feet across, a moonlet in a binary system, which made its orbital change easier to detect. Redirecting a much larger, solitary asteroid like Apophis, or a truly massive object, presents a different scale of challenge entirely. Scientists still debate the optimal strategy for deflecting truly colossal asteroids, weighing the effectiveness of kinetic impactors against the potential for more powerful, but also the lead time required for such an intervention also remains a critical factor. The earlier we detect a threat, the less energy and effort are needed to divert it. This necessitates robust asteroid detection and tracking systems, a continuous vigil across the solar system. The legacy of Apophis, therefore, isn't one of lingering fear, but of profound foresight. It ignited a global commitment to planetary defense, pushing us to develop the tools and strategies necessary to safeguard our future. DART then showed us that those strategies are not just theoretical constructs, but tangible capabilities proven in the cold vacuum of space. We are no longer passive observers of cosmic fate. We are active participants in shaping our destiny, armed with scientific knowledge and the will to apply it. The journey from a perceived threat to a proven defense mechanism underscores our evolving understanding of our place in the universe, a place we are now learning to protect, not just for ourselves, but for generations to come. As we've journeyed through the cosmos, exploring everything from the birth of stars to the intricate dance of planetary systems, you might notice a curious pattern in how we, as a society, perceive the vastness above. Our human fascination, it seems, often gravitates towards the exotic, the distant, the unknown. This brings us to a peculiar paradox: the media noise versus the real risk. You stand on Earth, gazing up at the night sky, and you might recall the flurry of headlines surrounding objects like Comet Atlas. For a time, it was hailed as a potential great comet of 2020, a dazzling spectacle promising to outshine even the brightest stars. News outlets buzzed with anticipation, tracking its trajectory, predicting its brilliance. Yet, as with many such celestial promises, Atlas ultimately fragmented, dissolving into a diffuse cloud, a spectacular bust rather than a brilliant show. The media, having built the hype, quickly moved on. This pattern repeats with truly interstellar visitors, like the enigmatic Oumuamua, which captivated imaginations with its bizarre shape and trajectory, even sparking speculative whispers of alien technology. The allure of the truly alien, the object from beyond our solar system, is undeniable, feeding a primal human hunger for discovery and wonder. But while the world's attention was fixed on these distant, often fleeting phenomena, quietly, relentlessly, Other objects closer to home continue their orbital ballet. Consider asteroid Apophis. Unlike the distant, ephemeral comet Atlas or the one-off interstellar Oumuamua, Apophis is a substantial near-Earth asteroid, measuring about 340 meters across. Its initial discovery in 2004 sent a shiver through the scientific community. Calculations revealed a startlingly high probability of impact with Earth in 2029, earning it the ominous nickname God of Chaos. This was no distant, unverified threat. This was a tangible, colossal rock on a potentially collision course. Yet, for all its genuine, albeit later revised, threat, Apophis rarely garners the same sustained media frenzy as a potential great comet or an alien probe. Its story is one of meticulous, painstaking observation and calculation, a testament to the quiet dedication of planetary defense scientists. Here's the key scientific fact. While interstellar objects like Oumuamua offer invaluable insights into other star systems and the processes of galactic travel, their direct threat to Earth is statistically negligible due to their rarity and typically high velocities. In contrast, near-Earth asteroids like Apophis, though less glamorous, represent a far more concrete and immediate, albeit still low probability, risk. The media, driven by novelty and spectacle, often prioritizes the sensational over the statistically significant. It's a quirk of human psychology, perhaps, to be more captivated by the truly unknown and exotic, even if it's harmless, than by a known, quantifiable, but less dramatic risk. And this brings us to an academic tension. While some scientists advocate for greater public awareness and funding for planetary defense missions, emphasizing the very real, if infrequent, threat posed by NEAs, others argue that the public's fascination with interstellar objects provides a crucial gateway for inspiring interest in space science overall. They suggest that the wonder generated by Oumuamua, even with its speculative tangents, can lead to broader support for astronomical research. The debate centers on how best to balance public engagement with the sober reality of risk assessment and mitigation. Should we lean into the awe-inspiring, even if it's not the most pressing concern? Or should we consistently highlight the more grounded, potentially life-saving work of cataloging and tracking near-Earth objects? The quirky detail here lies in the evolution of Apophis's perceived threat. Initially, its risk was so high that it briefly reached level 4 on the Torino scale, a scale for categorizing impact hazards, indicating a threatening encounter. This was unprecedented. For a brief period, humanity faced the very real prospect of a city-destroying impact within a generation. Subsequent, more refined orbital calculations, incorporating additional observational data, thankfully reduced its risk to 0 for 2029, and later for 2036. However, its close pass in 2029, where it will come closer to Earth than some geostationary satellites, remains an extraordinary event, offering scientists an unparalleled opportunity to study a large asteroid up close without the need for a costly space mission. This close approach, a mere 31,000 kilometers from Earth's surface, will be visible to the naked eye from certain parts of the world. A silent, swift reminder of the cosmic shooting gallery we inhabit. So, as the media chases the next great comet or speculates on the origins of the next interstellar visitor, the quiet work of planetary defense continues. Teams of astronomers, like cosmic sentinels, tirelessly scan the skies, cataloging every known NEA, refining their orbits, and calculating potential risks. It's a less glamorous story, perhaps, but one that speaks to our collective responsibility, not just to understand the universe, but to safeguard our place within it. The fascination with the distant and unknown is vital for discovery, but the vigilance against the known and near is paramount for survival. As we've journeyed through the vastness of space, exploring cosmic phenomena, you might naturally assume that the greatest dangers lurk in the most colossal objects: a giant rogue planet, a massive black hole, or an enormous comet from beyond our solar system. These are the stuff of cinematic catastrophe. Yet, as with so many aspects of the universe, reality often presents us with a profound irony, challenging our intuitive sense of scale and threat. Consider the interstellar visitors we've encountered, like Oumuamua or Borisov. These are truly alien objects, originating from the cold, dark reaches between star systems, traveling for eons before briefly gracing our cosmic neighborhood. Oumuamua, for instance, was estimated to be hundreds of meters long, an elongated, cigar-shaped enigma moving at incredible speeds, far faster than anything gravitationally bound to our sun. It was a massive, truly foreign object, yet its passage through our solar system posed virtually no risk. Its trajectory was a hyperbolic slingshot, a one-way ticket, entering and then exiting, never to return. Its immense velocity meant it was simply passing through, its path barely perturbed by our sun's gravity, certainly not enough to steer it towards Earth. It was a cosmic giant, but ultimately a harmless passerby. Contrast this with the much smaller, seemingly insignificant pebbles that perpetually orbit our sun. Within our own solar system, in the main asteroid belt between Mars and Jupiter, or out in the more distant Kuiper belt, reside countless rocks. Many no bigger than a house or a small mountain. These are the objects that truly keep planetary defense scientists awake at night. The key scientific fact here is that an object's danger isn't solely determined by its mass or size, but critically by its orbital dynamics relative to our planet. An interstellar object, by definition, is not gravitationally bound to our sun. It's just a transient visitor. A solar system object, however, is locked in an intricate dance with the sun and its planets. Its orbit, subject to subtle yet powerful gravitational nudges. This brings us to a quirky, lesser-known detail. Jupiter, our solar system's colossal guardian, while often deflecting potentially hazardous objects, can also be a cosmic billiard player, subtly perturbing asteroid orbits over millennia. Its immense gravity can, in specific circumstances, act as a slingshot, flinging objects from the main belt into Earth-crossing trajectories. These are not objects traveling at interstellar speeds, but rather at velocities that make them susceptible to the gravitational influences of the inner planets. They may be smaller, but their paths are intertwined with ours, making them far more probable threats. The infamous Chicxulub impact, which ended the reign of the dinosaurs, was caused by an asteroid, estimated to be around 10 to 15 kilometers wide, a mere pebble by interstellar standards, but its orbit was such that it was on a collision course with Earth. The academic tension here lies in the ongoing effort to precisely map and predict these threats. Scientists still debate the long-term stability of certain asteroid families and the precise mechanisms by which objects are perturbed into Earth-crossing orbits. Some theories suggest that certain orbital resonances with Jupiter act as escape hatches, pushing asteroids into chaotic paths, while others emphasize the cumulative effect of countless minor gravitational interactions. The sheer number of near-Earth objects, NEOs, that we track, numbering in the tens of thousands, highlights this continuous challenge. While we have identified most of the truly massive, planet-killing asteroids, the population of smaller, city-destroying objects is still largely uncatalogued. So you stand at a crossroads of cosmic understanding. The truly gargantuan, interstellar wanderers are mostly just spectacles, their immense speeds carrying them safely past us. Yet, the smaller, gravitationally bound rocks, the cosmic detritus of our own solar system, are the genuine concern. Size, it turns out, is not the only measure of danger. Context, velocity, and the intricate ballet of gravity within our home system are far more critical. The universe, in its boundless wisdom, often hides its most potent threats, not in the grand and obvious, but in the deceptively familiar. As we've explored the intricate dance of celestial bodies and the potential for cosmic encounters, a crucial question emerges. How do we ensure we're never caught off guard again? The answer lies in an unwavering gaze towards the heavens, a continuous, tireless watch. You might imagine solitary astronomers peering through eyepieces, but the reality is a symphony of automated observatories, scanning the sky with an efficiency unimaginable just a few decades ago. These are humanity's vigilant eyes, constantly sifting through the starlight for any sign of a rogue visitor. From distant comets to more immediate near-Earth objects, or NEOs. Take Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System based in Hawaii. Its powerful telescopes don't just take pretty pictures. They systematically map the night sky, repeatedly photographing vast swaths of it. By comparing images taken at different times, sophisticated algorithms can detect anything that is moved, a telltale sign of an asteroid or comet. It's like a cosmic spot-the-difference game played on an epic scale, but with potentially world-saving stakes. Pan-STARRS has been instrumental in discovering a significant number of near-Earth objects, including many that were previously unknown, quietly charting their paths through the solar system. Its mission is relentless, a digital sentinel against the vast unknown, contributing to a global database that tracks these celestial wanderers. Every night, millions of stars and galaxies are imaged, but the real prize is that faint, moving speck, often no brighter than a distant star, yet potentially carrying the weight of a planet's fate. Similarly, the ATLAS system, the Asteroid Terrestrial Impact Last Alert System, also operates with an array of telescopes, but with a slightly different emphasis. While Pan-STARRS is designed for wide, deep surveys, ATLAS specializes in a more rapid, all-sky scan, focusing on objects that might be on a collision course with Earth in the very near future, days or weeks rather than years. It's the ultimate early warning system, designed to give us that crucial heads up, even if it's a short one. Imagine these observatories not as individual instruments, but as nodes in a global network, each contributing its unique perspective to build a comprehensive picture of our cosmic neighborhood. The sheer volume of data they process is staggering. Gigabytes upon gigabytes of celestial information, all analyzed by intelligent systems looking for that one tiny moving pixel. These automated sentinels don't just detect, they immediately calculate preliminary orbits, flagging any object that comes within a certain proximity to Earth. This rapid response is critical, as even a small, undetected object could cause devastating regional damage. As history has shown with events like the Tunguska explosion. But the future of this celestial guardianship is even more ambitious. Soon, the Vera C. Rubin Observatory, perched high in the Chilean Andes, will begin its operations, revolutionizing our ability to map the dynamic universe. Unlike traditional telescopes that focus on small, specific areas of the sky, Rubin is designed for a truly monumental task: to image the entire visible sky every few nights. Its massive 8.4-meter primary mirror, an unprecedentedly large 3.2 gigapixel digital camera, will collect an astounding 20 terabytes of data each night, creating a movie of the universe, a continuous, time-lapse record of cosmic change. This isn't just a bigger telescope. It's a paradigm shift in how we observe, offering a depth and breadth of coverage previously unimaginable. It will allow us to detect fainter, smaller objects with greater speed, track their movements with unparalleled precision, and build an unparalleled catalog of celestial wanderers. The goal is clear: to ensure humanity is never again blind to future Apophis-like threats, or even smaller, more numerous objects that could still cause significant regional damage. This ongoing watch transforms our vulnerability into vigilance, providing the lead time necessary for potential mitigation strategies, from evacuation plans to deflection missions. Yet even with such advanced technology, the cosmos remains vast and full of surprises. Scientists still debate the optimal balance between discovering entirely new objects and refining the orbits of known ones, especially those with complex gravitational interactions from planets like Jupiter, which can subtly alter trajectories over decades, making long-term prediction challenging. The sheer computational power required to process and interpret this deluge of data, and to prioritize potential threats based on their impact probability, is an academic tension that drives continuous innovation in machine learning and data science, pushing the boundaries of what's possible. The quirky detail in all this lies in the subtle art of detection, particularly through the light curve of an asteroid. An asteroid doesn't just appear. It reveals itself through the way its brightness changes over time as it tumbles and rotates. These minute fluctuations, meticulously recorded by our observatories, can tell astronomers about its irregular shape, its spin rate, and even its surface composition, offering a unique fingerprint for each cosmic traveler. Sometimes, A false positive can even be a piece of space debris or a satellite, requiring careful verification. It's a silent, visual language spoken across billions of miles, and our observatories are learning to interpret its every nuance, aided by dedicated teams of human astronomers who perform crucial follow-up observations, confirming discoveries and refining orbital parameters. This continuous monitoring, this tireless watch, is more than just science. It's an act of collective foresight, a testament to our growing responsibility for our own future in a dynamic and sometimes unpredictable universe. Atlas, that initial cosmic whisper, proves to be a harmless, beautiful passage. But Apophis, the god of chaos, was our dress rehearsal, a cosmic near miss that sharpened our focus. It underscores a profound truth. Planetary defense isn't science fiction. It's a vital, ongoing mission. Scientists continue to refine models, debating the most effective deflection technologies, knowing that out in the cosmic ocean, truly unknown threats always await discovery. This isn't about fear, but about preparedness, a collective awakening to our place in a dynamic universe. And perhaps, in understanding the patterns of our planet and our universe, we begin to understand ourselves.